Okay, hey everybody, welcome to, I guess this will be video solution number 2. I'm sure I'll lose count here. But a lot of you have been asking about chapter 23, number 20, what was this, 26. And so why don't I kind of work through this? This was kind of a neat one. And maybe I should begin by reading the problem here. Although I think you know it. Here it says that the electric field along the axis of a uniformly charged disk of radius r and of total charge q was calculated in example number 8. All right, so let me just try to draw a little disk here. I hope that sort of looks like a disk to you. And then say that, out here some distance away, let me call it distance x, and the disk has a radius of capital R. This example, number 8, worked out the solution for that. And so go back and I'm looking at the page number here. Where is it? 659. They work out the solution, and they come up with this. They said at this point right here, the electric field would be along the x-axis, so electric field along the x-axis, and it would be given by this equation, 2 pi times Coulomb's constant times sigma. Now, hopefully what you caught in the reading is the sigma is kind of the traditional symbol for the charge per surface. So this would be how much charge is spread over this disk. So in other words, sigma would be the q, the charge on the disk, so I'll just put a little q, and then divided by the surface area, which would be pi r squared if you have this thin little slice, maybe looking like a quarter or something. Okay, so that's our sigma. Of course, the rest of the equation then is 1 minus x, and let me pause there just to remind you, the x that was worked out, this is the x, this is the distance from the center of the disk on a line of symmetry coming out, so there's the x. And then we have the r squared plus the x squared to the 1/2 power. And if you got a chance to go through my first video, I think even a harder problem, number 26, that was part B on there, where we started with that and added up a bunch of disks. And I had made that comment, and I'm going to repeat it here. Make sure you're doing more than just doing the math. You're reading the math and what these symbols mean. So I want to always start a problem with saying, hey, this is what we should be reading. The charge on the disk, the distance along the axis of symmetry from the disk, the radius of the disk. And so regardless of what symbol we use, the equation hopefully makes sense more than just symbols and more than a plug and chug, because as I said in the other video, and we'll keep saying it, is that a lot of these problems, half of it is done with the physics and really understanding the meaning behind the electric field. Where does it come from, and the symbols that are portrayed in the equation, and then actually doing the math. And so you can only do about half of the necessary steps if you only do the math and if you're looking for a kind of a plug and chug answer. All right, so that's the electric field from a disk, and like I said, that was back in the book there. And so the problem then goes on to say, show that the electric field a distance x that is large. And so what they're saying here is if you're really far away, way over here somewhere, so this distance is x, that this would basically look like a point to you. In other words, if you are so far away, you may not be able to tell that that's a disk. It might just look like a point. And one of the things that hopefully you got out of this first step of this chapter, the easy one, is this is the equation for the electric field from a point. That is, if I just had a point right here of capital Q, and I was some distance out here, R, although maybe I should call it X to match this problem, I would have an equation that looked like this. And so the physical argument is that if you got far enough away from this disk, it wouldn't look like a disk, it would look like a point. And therefore, this equation, which is the equation for a disk when x is really large compared to the radius of the disk, must look like that. In fact, I would even go further to say that whether we have a disk, whether we have a ring, whether we have a rod, if your distance is really far from it, it'll physically always look like a point. You're just so far away from it. So the limit of all of our equations for the electric field of all these shapes we've been working with, whether they be a ring or a disc or a rod, would come out to be this. So this question could have asked it about any shape or object. A cube really far away looks like a point, as I said, a rod or I don't know what other crazy shape, a dodecahedron really far away looks like a point. So it doesn't really matter what the object is. You get far enough away from it, every equation for that particular geometric shape should, in the limit, look like that. Okay, so let's give it a try. And so kind of the key here, and they kind of help us with a little hint in using the binomial expansion like they did a couple times in the reading. Let me try it here. And let me start with just this part of it. The x over r squared plus x squared to the 1/2 power. Because if you say something like x is much, much greater than r, you are essentially saying, dividing both sides by x, that the number 1 is much greater than r over x. So this ratio r over x is a really small number. So I'm going to take advantage of that right in here. I'm going to factor out an x squared. And when I do that, this term here becomes an r squared over an x squared, and of course that just becomes a 1. And of course then we can, let's put equals over here, I'll break this into two parts. I'll leave the x upstairs, but this x to the 1/2 power is just an x, and I still have a 1/2. And I'll change the order here, so this is 1 plus an r squared over an x squared. And then, of course, now the x cancels off, and you get a 1 over a 1 plus an r squared over an x squared to the 1/2 power. Keeping in mind that that number is, this r over x right here, is much less than 1. In fact, if it's much less than 1 and then we square it, as we're doing here, it's even more less than 1. So this is significantly less than 1. Because if you go back to Appendix B, or if you just want to Google, and I saw it in Wikipedia, somebody else was asking, so I sent them a link to the binomial expansion. But if you have something that looks like this, 1 plus something, raised to the n power. Now your author here in this problem gives the small Greek letter delta, okay. But it would be equal to 1 plus n delta plus n minus 1 over 2 factorial delta squared, and it keeps going. And if you want to do this expansion, go ahead. Those of you who might remember your Taylor series, I find this a little bit easier with a Taylor series, which says you could take any function, and if you take its nth derivative evaluated at some value a divided by n factorial, and you sum it up from n equals 0 to infinity, and then x minus a raised to a factor of n. And so if you go through this, in other words, when n is equal to 0, so no derivative evaluated, and if you set in this problem a equal to a, you will get all of these terms in the binomial expansion. You don't have to do something as hard as the Taylor series to do this. You can just go back to the binary expansion. But I like Taylor series because they work all the time. And so I kind of forget, to be honest, about binomial expansions and just jump to a Taylor series. So either look in the book back to Appendix B. They have a nice math review there. Actually, I think they just give you the results. They don't even go through the math. So maybe you want to dig up your Taylor series from your math, and probably is Math 160, late in Math 160. Not sure where you guys hit the Taylor series. But in either case, I want to show you something very interesting that we're going to use a lot, and you've already seen it a few times, is that if you have something like this and you expand it out in a binomial expansion or a Taylor series, and this delta is small, that's the key. Remember, we're small, and you start raising it to a power, that's the big key, because right here, you take something that is small already and you raise it to a power, it's even smaller. So this next one would be even smaller, and the next one would be even smaller still. And since each one gets progressively to a higher power, that's where this part of the Taylor series comes in. It gets smaller and smaller. And so if you take a number like 100th, this is 100th, but when you square it, it's 1/10,000th, and then this is 1/1,000,000th, and this is 100,000,000th. So these are so small, you can say, don't count them. And so that's why your author is saying here, and so I'll just kind of do a little math review, that if you have something that looks like this, you can kind of simplify it and then just write it equal to that. And you could only justify that if the case is that in this case, delta is much less than 1. And that's what we have here. Okay, so doing this little math review, let's apply it back up here. And so maybe I'll put page number 1 there and kind of shift this up and pull it down so I can see a little bit of page 1 as I go on to page 2. And so coming back here and rewriting this as, and I'll write it in the numerator now, 1 plus, and so bring this up into the numerator, and I'll have an r squared over an x squared to the negative 1/2 power. And again, putting together that this is a binomial expansion with the condition that this number is small, I can write this as 1 plus, and then it says what power it's raised to, which is a negative 1/2. And then this delta, and that is an r squared over an x squared. All right, so now let's come all the way back here to page 1. Let's rewrite this equation. And so this is saying here that the electric field, maybe I'll put it down here so you can kind of see it on the video. But if you're really far from a disk, the electric field would be 2 pi Coulomb's constant times sigma, 1 minus, and so there's that quantity that we just worked out. It would be 1 plus a negative 1/2 r squared over x squared. Okay, so like I said, this would now be an equation for the electric field from a disk if you put in the condition that you're really far from it. And so now if we simplify it, well, we still got the 2 pi and Coulomb's constant and the sigma. 1 minus 1, that goes away. The negative here and the negative here now make a positive. We then have the 1/2. We now have the r squared, and we now have the x squared. And so I'll put the 2 pi Coulomb's constant. Let's go back to the sigma. Going back to our discussion here on page 1, the sigma, the charge density on the disk, is the charge on the disk divided by its area, pi r squared. So this would be Q over pi r squared. And then here is the 1/2, here is the r squared, here is the x squared, and lo and behold, a lot of things cancel appropriately. And we're left with Coulomb's constant times the charge on the disk in the numerator all over the distance squared. The argument that we made must be the electric field when you are really, really far away. Ta-da! It worked. I'm glad.